So Professor Nithin Nagaraj has been kind enough to not volunteer for this slot, but whom I have volunteered for this slot, but he didn't protest. So he's going to spend
little bit on this and
a
then
little bit of time on this. Then we will come to the actual talk about video. We will start off with the and very good. When you switch, you just tell them.
I'm doing. Yeah, thank you, Professor Neelima. So we are back for the second and the last time, right? I thought I'll briefly spend some time on this principles of machine learning, not too much time, because there are mistakes and pitfalls which I myself have committed, and I want to share some of those lessons. So we don't have to go in great detail, but I think it will be useful for anyone using machine learning to sort of go through it. I mean, so you know that today machine learning has conquered pretty much everything, right? Physics and chemistry you already know, right? The Nobel Prize in physics, of course, you already know, but chemistry also, right? AlphaFold, for example, you know that predicting the 3D structure of the protein from the amino acid sequence using, I think, reinforcement learning and stuff like that. Jumper and Hasabees, right? Google DeepMind, right? So, and then of course, what is very interesting is that they had won, Jumper and Hasabees had won the Lasker Prize the year before. And it's interesting that Lasker Prize is one of the key awards in medical sciences, actually, and it's second only to the Nobel Prize. And the thing is that people who win the Lasker Prize typically go on to win the Nobel Prize, which is what happened here as well, you know. So chemistry, physics, biology is conquered. Math is not far behind, right? There are all these machine-assisted proofs and stuff like that. So we already know the buzzword, yeah. But I thought, I mean, nothing, I won't go into any great detail for the history of AI, but it's actually very interesting to note that it started off in 1956, this famous Dartmouth research, summer research project. I would imagine, you know, something like this, maybe a small set of people sitting in a cozy, dingy room, you know, doing a discussion meeting and, you know, and talking about AI. McCarthy was a computer scientist, and you probably know Shannon and Minsky, right? Yeah. And interestingly, the AI word was coined. I mean, you can go and look up the document, and they talk about AI, and later it became cybernetics. The word changed to cybernetics for a brief while, and then it was now replaced by ML, DL, data science, and all that. Now, if you go to the document itself, it's interesting. It's available on the internet. The paragraph is quite prophetic, actually, right? It says that the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that the machine can be made to simulate it. I mean, it's very prophetic, right? Because we're talking about a protein, predicting protein structures, then we're talking about climate models and all kinds of stuff. So pretty much that's what they're saying, right? And they're talking about language, form abstractions, concepts. So it's very, very, I think, I mean, they're able to, I mean, see like nearly 20 years since then, right? Yeah. I mean, actually much more than that, right? This is actually 1950s, but this particular one is 2006, but yeah. Okay. So yeah, broadly, I think we know that it's a set of approaches to create machines with intelligence. Now, if you look at AI as a field itself, right, it's actually an anarchy of methods. This is a good way to look at AI, you know. How do you sort of organize the whole discipline? Broadly speaking, there are three broad divisions. I mean, this is actually not very, they're not really rigid boundaries, but you can say that one is based on deductive logic, like if-then statements, right? Fuzzy logic, decision trees. The middle one is based on inductive logic, right? Computational statistics, sort of learning from data. The third one is interesting. The third one is what's called subsymbolic AI, which is sort of inspired from the brain, biology inspired. So roughly it falls in these three bins, and your favorite algorithm will be one of these and a combination of them. So this is the way to look at the field. And then of course, if you look at the buzzword, right, you have pretty much you know, all kinds of words like ANNs, LLMs, PCA, you know, all these acronyms are there. Yeah, so they all fall under machine learning. I mean, some things are excluded here, but again, this is not really a very hard boundary, anything like that. But yeah, all these fall in under classifying, clustering, reinforcement learning, deep learning, stuff like that. I think you're aware of this, I guess. Yeah. One important thing you need to remember is how does AI sort of differ from the Greek way of doing science, if I may call that way. You know, there's a very nice debate between Paul Dirac and Richard Feynman. You can look it up. So what is very interesting? Feynman tells Dirac that look, you're doing science the Greek way, which is based on axioms and theories and structures, and then you're going to formulate theories and then predictions and things like that. And Feynman says that he himself follows the Babylonian which is more the Indic form of computation or mathematics. It's not based on axioms per se, it's not based on axioms, but based on computational methods. Computational methods, techniques, recipes, algorithms, not on axioms. So there are these two broad schools of thought, and of course, there's sort of, there is an interaction between the two. Now, AI is more the second one, more the Richard Feynman, the Babylonian, the Indic. You go back to, I think you go back to Madhava and Brahmagupta, all the Indic mathematicians, right? Aryabhatta and all these other people. So Bhaskaracharya and things like that. So that school, what it says is data is the king, right? Experience, data, right? We don't really care about axioms and theories as much as data. Data is more important, and it's the god, the high priest, the king, and I don't really care about your theory if it does not agree with data. So, and this is important because you'll always see this tension between AI and conventional science and math, so to speak. They'll ask you, okay, how does deep learning work? Give me a proof. That's a very axiomatic way of thinking. I'm not saying it's wrong. I'm just saying that this tension is there because there is these two schools of clash of civilizations in some sense, you can say. But we can see that more and more we are moving towards the computational way of doing things. Even science, we're talking about climate science being taken over by AI. Not now maybe, but in another 5 to 10 years it may happen. It's happening already in some sense. So the argument here is that data is more important than your axioms and your models and theories and all that. Yeah. But of course, the truth is somewhere in between, right? I'm giving you two extreme pictures, but usually things are in between, right? Yeah. Okay, this is, I think, a diagram. I think Manish did a pretty good job in the first day, but I thought I'll recap this. How does traditional computer science work? Let's say that you want to identify digits here. You write a program and then you get the output, right? That's how traditional computer science works. But the problem in the real world is that this is not how real world problems are posed, right? Real world problems are posed in the following way, right? I give you a set of data, and then maybe I'm asking some question about the data, So I'm asking, for example, let's say that, I'm asking, okay, I have all these, this is just a cooked up example, you have maybe some, information about whether a particular decade was warm or cold. You already know it historically. And you want to know whether this particular decade, is it going to be warm or cold? I'm just cooking up this problem here. So we know the question, but we don't know how to write the program, So what the machine learning does is, okay, look, you know the past information, you know the labels, like this decade was warm, this decade was cold, this decade was cold, this decade was warm. Now please tell me what program will try and interpolate or do a curve fitting, fancy curve fitting between this set of historical data and the labels. And it actually makes sense, right? Because if you think about science itself, right? Let's say you look at an RLC circuit or a simple pendulum. These are systems which are easy to probably write down the equations, right? But real world problems, whether it's biology or climate, is so complex that you are helpless in some sense. You want someone else to do the work for you, maybe a computer, right? To probably figure out the equations, eventually, right? So in some sense, what we're saying is that real world problems are not, easily analytically solvable and, that you can write equations, right? So you want the program to figure it out, that's the argument. And so this is the difference between the two, right? In one traditional computer science, you write the program, you get the output from the data, and in the machine learning, you get the program from past historical data, right? That's what I'm saying. Yeah. So this is called supervised learning, and there are two distinct phases, right? There's a training phase where you figure out the program. It's too complex, right? The function which maps every decade, of temperatures, whatever global mean temperature or whatever, to the labels warm or cold. It's so complex with so many other covariates and all that the computer hopefully will figure out a program which we can't even understand what it is. It's a recipe. It's an algorithm. It's a lookup table maybe, and then we are going to just use that for the temperature, or whatever, given some information about this decade, and then we can predict whether it's going to be warm or cold. So this is the and this is called the testing phase, right? This is what the whole paradigm works. And there are other things. I think Manish did a very good job in talking about all of them. I'm going to skip these remaining ones, but you have unsupervised, you have semi-supervised, and you have reinforcement learning. So reinforcement learning, for example, is based on this notion of reward and punishment, right? So that's how we, teach kids many times, right? Or whatever. If they do the task the correct way, you reward them, and if they do the wrong way, you punish them. Something like that. Something similar is used here, Yeah. So this is how the data is organized, right? You have features along the columns, and you have the output along the last column here. And these are called the raw features, and this is the output here. And depending upon whether you have the output in terms of finite number of classes or an infinite number of classes, you either call it as a classification problem or a regression problem. That's the usual thing. Yeah. Just to give an example, you may have year as one of the columns, which may not be a feature, whatever it is, just the index here maybe. The feature itself could be some kind of a sea surface temperature with some trends removed, right? Whatever, like the 3.4 index or whatever, some anomaly or whatever, and then you have the rainfall in mm. So you might want to do a regression, or you may want to do a classification, depending upon. I can threshold this data, which I'm going to show later. I can say that do I have a above average rainfall or a below average rainfall? That can be two classes, right? And I can do a classification. So just to give you a very simple example, let's say that a very simple example, you have height and weight of some students in a class, and based on their class 0 is below 15 years and class 1 is above 15 years, and you have a whole bunch of weight and height, and you want to see whether you can classify whether they're below 15 years or above 15 years just based on their weight and height. You get a distribution like this, and then you do you break it into training and testing, right? And then you hopefully try and so you have all possible instances, and you have a target function. I mean, you have an unknown target function. The function hypothesis, right? Set of function hypothesis H stands for the models that you want to use. For example, H could be the class of all decision trees, or it could be the class of all SVM algorithms, or it could be the class of all random forest. It could be the class of all ANNs. So the hypothesis set is your favorite algorithm that you want to use, and you're asking which among them is the best fit between your labels and your input features, right? That's what you're doing. Of course, there are a whole bunch of algorithms. I think I'm not going to go into any great detail here. The shallow and deep model. This is not exhaustive by any means. You can see a whole bunch of algorithms here. I mean, just to give you an example, what you need to remember is that every algorithm has an assumption to it. Very, very important to understand, right? So one of the simplest algorithm that you can actually do is a k nearest neighbor algorithm. And so the moment you choose the algorithm, the hypothesis class, you're looking for what assumptions does the model make, right? The model in this example, let's say that you are the average of the 5 people you spend time with, right? Whether you're spending time with security personnel, police people, guards, whatever, or you're spending time with people in the lab and people working with charts and instruments, whatever, So you can sort of, the argument here is that, so this is an assumption we're making. This assumption may or may not be true with the data, right? So we can use this assumption and we can find, so what we're saying here is that each of those classes, the nearest neighbors have similar features, and we can do it in an LP norm kind of a way, right? You can define the distance between 2 points in the class, and then you can ask how many k is the number of neighbors, right? How many should we take? This is just a mathematical description of this, which is not important. We can skip it. Now, what is important to understand here is that every algorithm has assumptions to be made. Like I made the assumption that neighbors belong to the same class, right? Neighbors in this having those in that feature space have the same class label. But along with that, you also have a hyperparameter. It's called a hyperparameter. K is the number of neighbors. How many neighbors to choose, right? 1, 3, 5, right? Whatever, right? So the point you need to remember is that you break the data into a training and a testing, and typically it's done 80:20, but you can actually vary this. And it's important that you don't even look at this testing data, right? You just keep it aside. And the training data itself, you now break it into, again, 2 parts, training part and a validation part. And you sort of rotate this, right? Because you want your algorithm to see every data instance. So your validation and training are sort of swapped around, right? So I mean, the blocks are here's a threefold class validation. So breaking into 3 parts, and 1 part is for validation, and the other 2 are for training. So what you're doing here is you're trying to figure out what is the best value of k. That's what you're trying to figure out. And once you're happy with that, then you can test it on the testing data, right? So this is how, I mean, you just do it for this algorithm, and notice this nice, interesting thing you get here, right? So this is called a decision boundary, right? So there's something very important to visualize if you can. Of course, it depends on the dimension that you have, that you will have a decision boundary between the classes, right? So it's effectively saying that anything on this side is class 0 and this side is class 1, okay? Now, the point you need to understand is that one is, of course, the way the machine learning model, I mean, the training testing does, I mean, the split. But the other things you need to remember, right? That what is very important is you can only test once. Just remember this. It's very important that I made this mistake myself before. The testing data should be locked in a box and kept somewhere. You should never look at it at all. 20%, you should never even touch it, and it should be randomly sampled from your data. Now, the sampling is also very tricky because if you have time series data, then the sampling should be chronological, right? You cannot sample. I mean, you'll have to maybe take the one which is the latest should be the testing data, right? Not so you need to figure out all this. You need to be very careful when you're trying to sample and keep the testing data. But what is important is that you're not allowed to look at the test data again and again and again. Okay, that you cannot do that. You can do the validation part. This part you can do any number of times, no problem. You can change your hypothesis class, SVM to something else and something else, and then there are all these metrics, right? There are all these metrics. Do you guys are familiar with the metrics? I'm not going to spend any time on the metrics, but maybe I'll just show you. Yeah, I mean the confusion matrix is very obvious, right? I'm showing it for 2 classes, but it's for n classes also. N cross n. It's an n cross n matrix where your true label and the predicted label, right? And obviously, then you're looking at the diagonals, right? And you want to maximize the diagonals, right? I mean the diagonal, and the ones on the other side are the you have the false positive and the false negative. This is a simple silly example here. But what is important is that you get other measures on so the confusion matrix actually completely captures the entire the power of your algorithm, right? Everything that you want to compute is from the confusion matrix. Just remember that, right? All things, your accuracy, precision, recall, sensitivity, specificity, F1 score, everything comes from the confusion matrix. So that's the most important thing. And then you have all these formulae here. But I think I'll just spend very briefly. It's very important because these definitions are there. You can look up the definitions. Okay, they're fairly straightforward. But what you need to understand is that you have to be very careful, right? Accuracy or precision people use sometimes, but that may give a wrong information. I'll give you an example. Let's say that look at this diagram here, right? Let's say that you're doing an RT-PCR test, for example. So you want to identify how many people are COVID positive, right? Now, what could happen is you could have a lot of false positives. Let's say you have a lot of false positives. The test is giving a lot of false positives, okay, but not so many false negatives. Let's assume that, right? So what does it mean then? That means that your accuracy and precision will be very bad, right? Your accuracy and precision will be extremely poor because the false positives will play a role in both the precision and in the accuracy. But what about the sensitivity? Look at the sensitivity, right? It's number of true positives divided by true positives and false negatives. So you could have a very highly sensitive test, RT-PCR test, okay, but it's very, very poor in accuracy and precision. And what does it mean? And why such a test is okay with us? Why is that? Because you don't really care about false positives. Okay, what would a false positive do? You're going to put some people in quarantine, though they are not really positive. That's okay, right? I mean, it is not good, but it's less of it is a discomfort they're going to face. But false negatives are very, very dangerous, right? Because if you just allow them and they're actually, I mean, you've wrongly classified them as negative, they're going to go and spread the virus. So you notice how there is an imbalance in your decision making, right? So accuracy or precision is not the way to go about it, right? Maybe you're looking for something which is highly sensitive. You want your algorithm to be very sensitive. You may not care so much about the accuracy or precision, I mean, in the initial stages especially, you may put a lot of people in quarantine. You don't really care. Because you're ensured that maybe your false negatives are very small, So this is very important to remember. And also one more thing you need to remember is accuracy is another problem. With accuracy is that if you have imbalanced data, right? Let's say that you have extreme events, especially in climate and other kind of problems that you're working on. Your extreme events, I mean, they could be a class, right? So the number of instances in that class can be very small, right? So the accurate, and the algorithm may completely do wrongly on that class, okay? But your accuracy will not be affected much because it's very small numbers, right? And other classes have large numbers. So this imbalance is there, To take care of that, you have this notion of an F1 score. And you can do the F1 score for every class and then take an average. It's called a macro F1 score. The F1 score is basically the harmonic mean between the precision and the recall. But just remember this. I'm just saying that these are mistakes that I have done in my thing also. So it's good to sort of see whether is it precision, is it accuracy, is it specificity? What is it that you want to look at? F1 score, macro F1 score. So all those things you have to be very careful about. So pay attention to that is what I wanted to mention here. Okay, there's something called the no freelance theorem. I mean, there's a lot of technical version to this theorem, but the folklore is sort of saying it in a very generic sense. Is that just remember that there is no algorithm which will work on all data sets, I mean, that's something that you need to remember, that every algorithm comes with certain assumptions that you're going to make, right? and you're going to pay a price for that. So you may want to know whether this assumption is okay or not, right, for your problem. So you're always going to pay a price, So that's the thing I want to mention here. Okay, there are a lot of other things. I'm not going to go into all the details here, but I think Ambika covered some things about pre-processing, like normalizing the data. Maybe do you want to make it standard normal, or do you want to just make the range 0 to 1, or do you want to get rid of the variance? I mean, all these issues are there, right? Do you want to do PCA? Is PCA the right thing to do? And PCA is very sensitive to the units, right? I mean, if you have millimeters and meters, I mean, so to be very careful when you do PCA, right? So that will completely change your PCA. If it's dimensionless quantities, it's fine. So all these issues are there. You have to be very careful about pre-processing, feature selection, then how much data is there, how much do you have, and missing data, how do you handle missing data? We talked about that. Yeah, one thing which is something which I found important, I mean, I realized it after making mistakes, is that you need to set your random seeds. I think even Amit talked about it before, no? That everything on a computer is pseudo-random. The random seed, you can set it in Python or MATLAB. Just set it to some number like 42 or whatever, because you want, and when you put the code in GitHub, people should be able to reproduce the results, Otherwise, you don't even know what the random seed you've used for running your algorithm, and you yourself cannot reproduce it. So it's very, very important that it becomes completely deterministic in that sense, that everything that you have in the paper, every plot, every graph, every statistic, every table should be reproducible by yourself actually to begin with. After 6 months, when you look at the paper, you may not be able to get those results. So that is very, very important, I thought. And I mean, at least I believe in putting it in GitHub, and then of course putting in the paper in archive, and so that you want many people to see it and catch bugs, and there may be mistakes, or they may improve upon it, those kind of stuff. And of course, it's model choice, right? You remember I told the k-nin we talked about, the k-nearest neighbor, that the assumption was that the neighbors in the class have similar features, right? That may not be true, right? Just some other thing may be important, right? So, for example, SVM, if you look at SVM, it makes the assumption that, I mean, the basic SVM at least, that it's linearly separable, right? The two classes are geometrically linearly separable. And if it's not true, then use a kernel or use soft margins and things like that. So all these, so you need to figure out, what kind of stuff you want to do. Yeah, I mean, there are some more things, and yeah. Okay, I think we'll go to the main presentation now. So there's just any questions on this? I think you probably are familiar with most of it, but I thought I'll put it out there, and then we can get into the main topic which I want to cover today. Okay, so just a recap, last time what I already mentioned this, that we sort of very briefly looked at it, right? That chaos has all these properties. It looks and feels like randomness, though we don't know what randomness is. See, many times randomness can also be defined in a sort of, in the cryptographic community, right? They define randomness in the following manner. They say, you have a whole bunch of tests you can do, entropy, a lot of tests are there. You don't really show that something is random. It's failure to falsify. So let's say you pass all those tests. All that you can say is, okay, we have not been able to show that it is not random. That's all we can say. We cannot prove it's random, of course. Again, for true randomness, I think Amit talked about all these things, that on-tick randomness or whatever, aleatory randomness, right? Or the kind of, which is sort of fundamental. Maybe you have to go for some quantum phenomena or something. Otherwise, everything is epistemic, or it is based on, maybe chaos-based randomness in the sense of unpredictability or uncertainty. But yeah, but at this point, I'm not going to prove it to you, but maybe we'll talk a little bit about it. But there is in a certain way you can argue that chaos is robust to noise and interference. I'll show some evidence for that, what I mean by this statement here. And then this is something that we discussed very importantly, right? The decimal map, you remember, right? That the three conditions necessary and sufficient are that dense periodic orbits. So in the case of the decimal map, it will be that every initial value being a rational number gives a periodic orbit. It's dense in the sense that every other real number can be approximated by a rational number. You take any number, rational number, whatever, you can always there's always going to be a number very close to it, which is rational, and you'll create a periodic orbit, right? So it's dense in that sense. You give me an epsilon, I'll give you a rational number close to that epsilon for that initial value, which will be periodic. And then sensitivity depends on initial value. Again, that's also very easy to see in the decimal map, right? Because take any number, it could be rational, it could be non-periodic, but very, very close to it, you will have a periodic orbit, for example. I mean, right? Or even if both are non-periodic, then they become completely uncorrelated, right? All these kind of things are there. And topological transitivity also, I told you, that you take two non-zero measure sets in your domain, you'll always find an initial value with a finite number of iterations will visit the other one. You start from the first guy and you will visit the other one. a finite number of iterations. That's transitivity and is related to ergodicity. And anyway, so that we saw. So what I want to do today is sort of try and develop this paradigm that we are calling as neurocurious learning. The word neurocurious itself is, it's not that we coined this term. This term is already there in the literature, but we have borrowed this term, and I'll give you the context of it. But it's actually brain-inspired machine learning. That's what we want to say it. And okay. And usually what I do is when I give a machine learning talk, I say that all the slides were made by a human being, and no slides were made by and any resemblance is just coincidental. So ChatGPT was not used. And then I know it's funny, but maybe you may not laugh at it in the next few years. That no robots were harmed during making of these slides. I think we'll have to probably take it seriously in the next few years. I think the way things are going, right? Okay. So this is the plan. Let's try and see how much we can cover. So in the end, I'll show you certain. Again, a very very preliminary work that we have just started in trying to predict the monsoon. It's way very preliminary work, but some interesting, encouraging results are there. But the key equation for today's talk is that in some sense, chaos and noise together can lead to learning in some very interesting sense, and we'll see how that's the case. Okay, so this is something that we saw, right? That look, you have this AI, ML, deep learning, and then you have ANNs, which is sort of similar to the brain in some sense, not in an exact sense. And deep neural networks, they have all kinds of applications. I'm not going to list them, and they also have a lot of problems too, right? That we know that they're very data hungry, right? Deep learning is something which requires enormous amount of data for training, and that leads to overfitting. And the main problem is it's not easily interpretable. I'll have something to say about it later. And the heavy computing resources, and then it does not preserve causality. I'll tell you in what sense as we go along. And trustworthiness is also low. Again, I'll show you some valid ways to sort of measure this in some sense, if we can say it. Okay, how many of you have used ChatGPT here? ChatGPT or any LLMs, Bard? Okay, yeah, me too actually. Okay, so all these guys are there, LLMs, right? Now, the thing is that I wanted to give you why am I bringing this brain-inspired thing? So I want to sort of motivate you towards to that. So let's talk about the cost of ChatGPT. Scary numbers actually. 175 billion parameters. It has one. So it's actually a deep neural network. Essentially, it's a deep neural network. Attention and transformers, these are all fancy names, but there are mechanisms which are used. But essentially, they are deep neural networks with huge number of layers and the number of parameters, weights, biases. You count all of them. It's 175 billion. You require 300 billion words for training it. Okay, 4.6 million words for training. Dollars for training. This is the amount that they've spent. This is insane, right? And the running cost. Remember to run it, right? To run it. The testing obviously is faster, relatively speaking, but you still have to go through the 175 billion parameters. Remember that when you give a prompt predicting the next token, you still have to pass it through the entire 175 billion parameter network, and then you get the next token, right? So you have to maintain all these servers, right? Apparently they use 10,000 GPUs for training it, and there's a rough estimate. There are some nice papers on this, by the way. I don't have the reference here. Some 1,200 megawatt hours for training, and the power. So this is very interesting. If you look at the electricity consumption of ChatGPT, right? This is scary. It's equal to 180,000 US household electricity consumption. That's the number that they come up with. And what is even more scary than all of this is there was a study in 2019. Okay. University of Amherst did this study. This was on the GPT 3.0, not 3.5 or 4, of course, because 19 it was not even there. They showed that this is actually in the MIT. There's actually a detailed archive paper as well. They talk about how they estimate all these numbers and all that. The amount of carbon that is emitted in training a single training we're talking about just once, training a deep neural network like a ChatGPT or LLM. It produces 626,000 pounds of planet warming carbon dioxide, and it's equivalent to 5 American cars run for their entire lifetime. And the other numbers I can give you, you can look it up. There's an archive paper here. So a human being consumes like 11,000. Emits equivalent of 11,000 pounds of carbon in 1 year, and the transformer, the large language model, is orders of magnitude higher. So this is something important to remember, and this actually this motivates me to quote this. So you recognize him? I think by now you should recognize this person, right? Yeah, who's this person? He's a Nobel laureate. He won the Nobel Prize this year in physics. Yeah, this is actually Geoffrey Hinton, right? Hinton, he's the one who, one of the godfathers of deep learning. And yeah, so this statement, right? The statement he made in, I think, 2018 or 19 in a conference, somebody asked him, what does he think about the whole field, about this deep learning and this particular paper, the backpropagation algorithm paper. And he said that my view is that we should start over all over again, And he said that hopefully some graduate student listening to me will get inspired and then start working. I'm paraphrasing him. And so the question is, so this thing I showed you, right? This is actually not the truth. So what is important to understand is that there is a fundamental gap between ANNs and the brain. And we'll look at that. That's where the brain comes in. So let's look at this. Okay. Can you guess these gentlemen here? Anybody here? 1943, they wrote a paper together. One is a neuroscientist and one is a logician. They came together and they wrote the it's called the McCall-Pitts neuron. You might have heard, no? MP neuron, right? So they came up with the first computational model of the neuron. Okay. And what is important to understand is essentially today, 2024, the neuron has not changed much. Some changes have happened, but really essentially the same neuron. Okay. You have the weights and biases, and then you have an activation function, right? That's all that you have. So the question is, maybe we should start all over again. Maybe we should not. As if we take Hinton seriously, can we start all over again? So I was thinking, okay, how far should we go? And then should we start from the Big Bang? Maybe, but that may be too much to expect, right? And okay, maybe let's at least go back 3.8 billion years. No, let's look at evolution through natural selection. If you look at evolution through natural selection, what is amazing is that if you look at the complexity of the neuronal complexity of organisms, right, in their central nervous system, in their brains. It's quite staggering, actually. It's quite staggering. So we're talking about 175 billion parameters of the ChatGPT, but look at these numbers here, right? The elephant has 5.6 billion neurons in the cerebral cortex. We're only talking about the cerebral cortex. We're not talking about the cerebellum, other parts of the brain, because much of the important processing happens in the cortex, right? But there are other, you can look at human beings is 16.3, So there is this thing. And if you want to compare the brain, you can only compare with the universe itself, in some sense, or the subset of the universe, the Milky Way galaxy. This is again a staggering number, right? That you have 200 to 400 billion stars, okay? And the brain has 86 billion neurons. Now I'm including not just the cerebral cortex, the cerebellum, medulla oblongata, everything. You look at the whole central nervous system, you have 86 billion neurons, but each neuron is connected anywhere between 1,000 to 10,000 other neurons, So the synapses, right? The connections are 100 trillion, So it's an amazing comparison, right? That in some sense, that all of us here, we all carry, more than a galaxy of connections, of neural connections, I tell this, to my students because there's no reason to get depressed, you're literally carrying a galaxy of neural connections, You're just not using it, so there's no reason to be depressed, or you just have to, if this cannot inspire you, what cannot, nothing else can inspire you, right? Okay, so, but that's not it. We'll see something more, Brain actually is the ultimate machine, in every sense of the term. Highly complex, nonlinear. It has extremely high amounts of neural noise and interference. Now, there's a nice PNAS paper which talks about estimating the signal to noise ratio at a neuronal level, And they come up with this number, minus 29 decibels we're talking about, It's incredible, right? There's no human-made engineering system which can compute reliably at this level of noise, and interference, right? Okay. And the other thing is there's also multiplexing. So not only is the synapses carrying information, multiple signals, information signals are piggybacked, the multiplexing is happening, not in the usual frequency domain or time domain multiplexing. We don't really understand how it's doing it, and this is very, very important, right? I talked about ChatGPT, right? 1,200 megawatt hour, whatever, right? The power consumption. Here, there's some computation that it's an approximate number. It's not an accurate number based on the metabolism and how much of the energy the brain consumes in a thinking activity. They come with some number like 12.6 watts. That's nothing, right? And very importantly, we don't know how it works, And I'm not saying this. Who is saying this? So, V.S. Ramachandran, the famous neuroscientist who's written this book, Phantoms in the Brain, he makes this comparison of neuroscience that it's still in the Faraday stage. What he means by this is, now Michael Faraday, of course, did a lot of good, amazing experiments connecting electricity and magnetism, but it was not until Maxwell who came up with the Maxwell's equation and who unified electricity and magnetism, electromagnetic theory, right? We didn't have a theory of electromagnetism. So what he's saying is that in brain science, we don't have a Maxwell yet. We don't have this unifying overarching theory, we still don't have that, which is actually a good thing in many ways because, I mean, much of our job security is maintained. Anyway, okay, so I mean, this usually I give this thing that look at this household. Think of every house as a neuron, and then you want to convey information from one house to the other house. But just imagine 10,000 other people around you are talking, this crosstalk and interference, and I mean, it's unimaginable, and it's doing this with low power, right? So the question is, how is it doing it? How is it doing it? That's a question we can ask. And okay, this is again showing you so I want to show you how deep learning will do. So we look at if you add noise to the deep neural network weights, right? And even when you reach 8 decibels, right, the accuracy just collapses, So here, so this is actually trying to I'm mapping the standard deviation of the noise that I've added to the weights in terms of the signal to noise ratio, and but around 8 decibels you just fall flat, the accuracy just falls flat. We're talking about in the brain, we're talking about minus 29 decibels, right? So there's no comparison here at all. Okay, again the same thing I'm trying to compare. Other thing to remember is yes, here. So what I'm doing is I'm taking a neural network, learning a classification task, a 2-class classification task. After I learn everything, I take the weights and I add noise to the weights, and then I see how will it do again,
The testing phase.
During the testing phase, yes, exactly. Correct, that's correct. No, what I did was I learned everything and then I added noise. You could do that also. I mean, that will be harder to learn then. I mean, this is a simple experiment I did. Yeah. I just trained it, I fixed the model, froze the model in that sense. I learned it and then I added noise to it. Yeah, the main thing you have to remember is that the brain has chaotic neurons. This is where chaos will come in a big way. And there are other things like, our brain is highly parallel, massively parallel, because you're talking about 86 billion neurons and 100 trillion synapses, right? And so many layers you have and modalities, you have different sense organs, I mean, different modalities coming in. We really don't, it's not necessarily digital or analog. We don't know how it works. I mean, the firing in some sense can be said as all or none, but the membrane potentials are continuous voltages, right? So there's analog, there's digital, there's biochemistry. I mean, there's all kinds of stuff happening. It's not that we really understand what model of computation it's using, Okay. And then of course we do counterfactual reasoning and stuff like that. So this is the point that we want to make, that there is this fundamental difference between the artificial neuron used in the ANNs. It's just doing a W transpose X plus B. It's just a linear operation followed by a bias term, followed by some activation function, which is nonlinear. But that's not how the brain works at all. The brain does not, I mean, at least to our knowledge, to the best of our knowledge, it does not use backpropagation. In fact, it doesn't even do this kind of stuff. It actually uses chaos. The nice set of papers here, 2001 and 2003, the two papers, is there chaos in the brain, part 1, part 2. They exhaustively look at empirical evidence of chaos in neural systems, single neurons, coupled neurons, network of neurons, and things like that. And in this paper, they coin the term neurochaos. They say that that chaos is at pretty much all spatiotemporal scales of the brain. That is one common feature of the brain, and they coin the term neurochaos. So we were inspired by this, and we said, okay, why not we just try and mimic this in our architecture? We'll forget about, like, we'll take Hinton seriously. We'll start over again. We'll throw everything away, and we'll start with taking a network with chaotic neurons. And we have a whole bunch of variations of it, but I'll try and give you some flavor of it. Okay, I just wanted to say that much of the work was carried by my PhD student Hari Krishnan. He's now in BITS Pilani. I mean, a whole bunch of other people. Over the last five years or so, we've been building this. I mean, we're still a long way to go. We're not claiming that this is the final answer or anything like that. But I'll just show you some results, and you can make up your mind how it fares. Okay, so the argument here is that there is chaos empirically found at all levels of hierarchy in the brain. There's enough evidence for that. Whole bunch of papers on that. Single and coupled neurons, and people also talk about that perception memory is probably processed through some kind of neural attractors. So chaos is like a neural code. It's useful for information transmission. And I remember I told in the beginning that chaos the claim can be made that chaos is robust to some amount of noise. We can make that statement very precise actually, but we'll see if we can get to that. And you recall last class, I mean the first lecture I talked about GLS neurons, right? I mean we already did that. So what we said was, okay, can we use the GLS neurons, the 1D neurons? Can we build a network out of them and then do machine learning? That's what we wanted to do. I mean, I talked about this in the first talk, so I'm going to skip them, right? Decimal map and the binary map, the tent map, right? And I also told you that these are special neurons because they have this amazing, these GLS neurons have this, GLS maps have this amazing thing that, if you define your partition very carefully and you get the symbolic sequence, the generating Markov partition, right? So then you can show that the Lyapunov exponent is equal to Shannon entropy. And here I'm using the logarithm to base 2 to make it exactly equal. Otherwise, there will be a constant of proportionality. And you can interpret the Lyapunov exponent as, or the Shannon entropy in this sense as the amount of information revealed about the initial value as you observe the symbolic sequence, right? Yeah, that's why it's bits per iteration, right? And then, of course, we've used this. So we've done some work where we've used this neuron to show that you can do optimal lossless compression. So you can actually use it for data compression. And interestingly, JPEG 2000 uses an algorithm called arithmetic coding, which is actually very similar to GLS neurons. It's very, very similar to that. So sometimes you can say that the chaos is already there in these algorithms. And there are a whole bunch of other applications. I think we don't have to go into this. I mean, I recently, I just wrote this paper where I talk about all the places where this map is used. This piecewise linear chaotic maps. They're very, very effective. They could be used in a whole bunch of pseudo number generators, cryptographic applications, data compression. I just showed you, logic gates and things like that. So we're going to use these neurons now. So we're going to use the skew binary map, skew tent map. And the method is very, very simple. This is the crux of the talk actually. So what we do is you have the C1 to Cn. These are our neurons, okay? And x1 to xn is the input data. So let's say that I want to learn 2 classes, right? I want to learn maybe cats and dogs, let's say, right? Cat images and dog images, right? So I'm going to feed in the cat images here, one after the other, and I'm going to train the network. I'll tell you what I mean by training the network. And after I do that, I'm going to pass the dog images and train the network. And then I'll get test data and I'm going to classify. How it works is each of these neurons has an initial membrane potential, Q. So it's waiting to fire. It's not yet firing, it's just waiting with the Q value. It's a number between 0 to 1. The moment the input comes, it starts firing. It starts firing and it'll keep firing until it recognizes the input. What I mean by recognize the input, let's say the input is, okay, I'll just show you the, let's go back here. Yeah. So this is the initial neural activity, okay? And let's say this is a stimulus, it keeps firing. It will stop the moment it comes in the epsilon neighborhood of the stimulus, okay? So notice that, so for example, in this example here, it's going above the stimulus, that's not counted. Here it's going below the stimulus, that's also not counted. Only if it comes epsilon neighborhood of the stimulus, then we say that it has detected the stimulus, okay? So go back here. So notice that in this example, for example, this neuron has detected the stimulus much shorter than this neuron or this neuron. So each of the neurons have variable firing length. They don't have the same firing length. So we take all these guys, we call them the neural trays, and what we do is very, very simple. We extract features from them. Either we can use it and pass it through traditional algorithms like support vector machines or whatever, random forests or deep, you can use any machine algorithm here, or you can pass these features through a simple classifier like a cosine similarity classifier. Because once you have learned the 2 classes, the features from the 2 classes, then you can just try and, so when a test data comes, that also passes through the same network. It will start firing, you extract the features and then you see whether it's closer to class 1 or class 2. That's all we are doing, Now the question is, what are the hyperparameters? The hyperparameters are, Q is a hyperparameter, the map is a hyperparameter, what map to use, Q is a hyperparameter. Then we also have other features like, we extract features like firing time, firing rate, entropy and things like that. So what we're actually doing is we're doing neuroscience, What we're saying is, this is like the brain of the machine. And these are the neurons inside the machine. These are the neurons in the machine. These are the neural firings of that machine. And we're doing neuroscience on top of this. That's all we're doing. Okay. And this is the paper that we have published. This is a 2009 architecture. And what is very important is, how are we guaranteed that we're going to stop at the stimulus? How do we know that we'll find the stimulus? Recall topological transitivity, right? That these maps are such that we'll always be able to find, with a finite number of iterations, we'll be coming to the epsilon neighborhood of the stimulus. And this epsilon is actually the one of the hyperparameters, how close you want to come to the stimulus. So the topological transitivity guarantees us, and universal orbits. What are universal orbits? They're orbits where they are like irrational numbers, in some sense, right? They will visit all neighborhoods. So think of, for example, you look at the number 0.1234567, all the natural numbers, That number in the decimal map will visit all neighborhoods, right? It's going to visit all neighborhoods by definition, So you can have, so we use this. So we use this thing and and then I'm just showing you, these are the features we extract: firing time, firing rate, energy, and entropy. And then we can either pass it through a cosine similarity measure, or we can pass it through other classifiers, And we've tried it on a whole bunch of data sets: MNIST, coronavirus data set, all these, cancer data sets and things like that. What we found is, consistently, that remember, we had to tune it. What I mean by tuning is we have to find the right hyperparameters, Q, epsilon, the initial membrane potential, the epsilon neighborhood that we have to tune, and the map also, what kind of maps to use. Once you figure out, when you tune it, what I mean by tuning is we are trying to maximize the separation between the two classes, That's what we're trying to do. So I'll just show you some results. So these are the data sets that we have taken. These are some of the data sets we have tried, and these are always standard data sets if you do machine learning. So they have different classes and they have different training and testing samples. 80-20% we have taken, and these kind of results we get. So these are the F1 scores. So we should not use accuracy because again it's imbalanced data set, right? We're using the harmonic mean between precision and recall. Higher the better basically, right? So and we're comparing with different algorithms, decision tree, random forest, AdaBoost. So actually if you look at it, I mean this is for one particular data set I'm showing here. So yeah, I think for some we don't do well. Haberman survival, I think it's a cancer data set, I think, I forget now. Yeah, survival mortality, I think, something about that. There we don't do really well, but others are not bad, like we get very high F1 scores. This FSDD is spoken digit classification, it's like somebody speaking 0, 1, 2, 3 up to 9, and we have to detect that, spoken digit classification, okay? And what is interesting is that we can also pass it through other, so we can combine our method with traditional methods, we can even combine it. And if we combine it, what we have shown is that we can boost the performance of those measures. Let's say, for example, look at what I mean by this is for this data set, if you just use our algorithm, okay, this is not a good example. Let's take this example. For this data set, if you use our algorithm, you get 0.845 as the F1 score. Whereas SVM and KNN, they do better, they do 0.993. So they beat us. But there are some examples where if you use AdaBoost and our method in conjunction, then you can boost the performance, and you can get this kind of 20.59% boost is there, So what we're trying to say is that you're using some algorithms already, right? I'm sure that many of you are using your own algorithms, right? Random forest or deep learning. You could use in conjunction with our method, and hopefully it can boost your method, That's the point I'm trying to say here, And we also did it on the low training sample regime. So what I mean by this is that you only train less samples, You don't look at the entire data set, right? Only randomly you take 10 samples for every class and you train it. And then maybe I'll show you another graph here. Let me just, yeah. So basically this is showing you that if you use only, the low training sample regime, what's the kind of boost you get, with different methods, decision tree, random forest. So for some data sets you don't get any boost, but for most data sets you get a boost, And we also tried it for coronavirus classification. So either you have a 2-class classification problem or you have a 5-class classification problem. And what is amazing is that we get extremely good results, like with one sample, this is like a few shot learning. With one sample, you can really do a good classification, and we do it with 1,000 independent trials so that we don't do overfitting, right? So we run this algorithm 1,000 times independently, and then we still get very, very good results. That means that the information is contained in just one sample, that you can distinguish between them. And even with 5 samples, we get very good accuracies, We're able to classify them. Okay, this is showing you the few shot learning, right? So it's showing you as you increase the number of samples per class, how does the F1 score vary, This is actually looking at images trying to classify malignant and benign tumors. So of course, deep learning will not do very well. This is a deep learning algorithm. I mean, it requires more data set, right? But machine learning algorithms all do well. And I mean, we are at the top here. I mean, we're really, machine learning algorithms do really well in this, kind of a regime. But of course, if you increase the number of samples, then deep learning will pick up. Okay, there are several properties which I'll not go into now. So we have shown that it can approximate any decision boundary. It's a very simple theorem. It's not very difficult to prove this actually. That given any decision boundary between the classes, the network that I showed you can approximate that boundary. Okay, this is actually shown for ANNs in 1980. Saibenko's paper in 1980. They show that ANNs can do it, but we can also do it. And importantly, what we found is I showed you GLS neurons, but you may ask the question, why don't we use a neuron which is biologically plausible? And we have tried that. We have used the Hinmarsh-Rose neural model in the same network, and it does similar. We get similar performances. We don't get very good performances. Again, we have to tune it and all. Tuning is again a tricky thing. But we found that it's an overkill. We don't need this kind of a complicated neuron to do the learning. Our GLS neuron is good enough, But it does work with this. So in some sense, you can do neuromorphic computing in that sense. You can have a chip which does this. Yeah. There are other properties which I'll skip. I'm not. So this is showing you. If you recall, I showed you the noise performance, right? That as you add noise, what happens to the deep learning? We did the same thing here. We trained our model. We added noise to the learned parameters. What we learn, we add noise to that. We also have a problem. We are nowhere close to the brain by any means. But what we found is that I think if you look at it here, right, with around 4 dB, we have 78% accuracies. Deep learning, 10 dB beats 40 to 59. So we are better than deep learning, but nowhere close to the brain. I mean, so notice that there is a fall off, there is a fall in terms of accuracy as you increase the standard deviation of the noise. Better than deep learning, but still, I think the brain is doing a lot more things, Yeah. So yeah, how much time should I take, Neelima? Yes. Do you want me to take 5 more minutes? Okay, we'll just yeah. Sure.
What do you think is the brain architecture doing different?
So one thing is the scale of things is one thing, and multiple modalities are there, right? Here I'm just doing a very simple task and a one-dimensional neuron, right? So there you have, I'll talk about it later. Heterogeneity of neurons also helps us also. Here I showed you homogeneous neurons. The brain actually has heterogeneous neurons. It has different neurons for shape and color, and they're all not the same. They're all chaotic though. They all have bursting, spiking, and chaotic behavior. That is known, but the neurons are different, So complexity and heterogeneity is one thing. There may be something more also which we're missing. We don't know. I mean, in the biochemistry, I'm not sure, but yeah. So one thing is stochastic resonance. We will talk about that maybe in another 5 minutes. I'll just try and see if I can. Yeah, this is about the noise. Okay, I think you guys are familiar with stochastic resonance, right? That usually we have this thing about if you have noise intensity and performance, right? A linear system will have a monotonically degrading performance as noise increases. Linear classifiers, linear systems actually for that matter. That's not necessarily the case with nonlinear systems. Not that all linear systems behave like this, but some nonlinear systems have this interesting phenomena where intermediate amount of noise is good for the performance. Low noise is not good, high noise is not good. Intermediate noise is good. That's the stochastic resonance, right? And I think there's a lot of interesting work going in this area. Again, there's an evolutionary example here actually. This paddlefish, right? This paddlefish is, it has this, the prey of the paddlefish it's called a zooplankton, Daphnia. Now, to detect this, it has this beak, right, which has these mechanoreceptors, okay? What is very interesting they found is that it's able to detect this Daphnia if there is noise. If it's no noise, it can't detect it, So the neural system is sort of tuned for noise, that ambient noise. For that noise, it's able to detect the Daphnia. The no noise, it cannot. High noise, it cannot. So this again, evolutionarily, it has sort of by natural selection, those paddlefishes which could use stochastic resonance survived, in some sense, right? Others could not, who couldn't use that noise, they could not survive, right? Something like that. Yeah. So this is very interesting, we thought, and of course, this cochlear implants, right? They found that cochlear implants, if you add noise, it helps in recognition. Again, very interesting. Again, yeah. So what is interesting is that in our method, you notice that epsilon I talked about, the neighborhood, that you're firing, it's firing. If it comes close to the stimulus, it will stop firing. That epsilon is the closeness, and that is actually stochastic resonance. We show this in this paper here, that we say that we have this resonance behavior in neurochaos. I'll just show you this thing. That look at it, if you have zero noise, right, you will never detect the stimulus because you will never hit the probability of hitting a real number is 0, right? And if you have high noise, right, you're going to detect very quick and you're going to stop. Your neural trace will be very short. You can't extract useful features out of it. It's intermediate noise which gives you intermediate firing. This is long firing, almost no firing. This is intermediate firing. So I'm just showing you this thing. So if you add, so what we're saying is that this is again going back to uncertainty, right? What Amit was talking about. So what we're saying is that the uncertainty in identifying the stimulus is good for us. If you have intermediate uncertainty, then as the noise intensity is intermediate, we get very good accuracy. Too low is not good, too high is not good. Intermediate uncertainty is good. So this is a case of stochastic resonance, and yeah, it becomes very high. It's just yeah. And we show it for this is an example of this the spoken digit classification problem, right? And what we find is we find multiple. So the thing is that we don't get the single peak, So we have like local stochastic resonance, right? So there is accuracy is good for different ranges of noise. It's not uniform. So that's another strange thing we're having. It's not convex. I mean, in the sense it has multiple maximas. Okay, this is something I don't have time, but there's a NeurIPS paper where we show that what we do better than deep learning is that deep learning. Okay, one is classification. We state of the art. We do comparable, but more importantly, we preserve causal structures. So if your data has causal structures, our internal representation also preserves causality. We sort of quantify the using Granger causality and stuff like that. Whereas LSTM, CNN, the internal representation, right, in the layers, there is no sense of causality. It's just a bunch of weights and biases. There is no, it completely destroys causality, It does classification very well, but so that's the difference between us because we are able to preserve causality. It's a very important feature. I think why the brain is also doing that, Maybe why the brain is not using a deep learning kind of a network, Okay, then heterogeneity, there's a whole thing about neuronal heterogeneity again, So that the brain has different neurons, different kinds of neurons for different functions, based on size, shape, location, and function. And we do the same thing. I mean, very simply, we can just have logistic neurons, and we can just add our input layer can have randomly chosen logistic neurons and GLS neurons in random locations, And we played with the amount, 25%, 50%, 25%, and we found that it does improve, that random. So if you add randomness, right, this stands for random heterogeneous neural class learning. It does improve. That's what we found, It improves quite a bit actually. Yes. In some cases, it's quite radical, Like this is a great example of So in many cases we do So we're sort of going closer and closer to the brain. We're making it. We made it chaotic. We made it heterogeneous. We made it random. So we're sort of. We're still very far away from the brain, but and one important thing, we studied what is the Lyapunov exponent of all the things because we were tuning it, right? In all cases there was chaos, chaos was necessary for learning. Especially the logistic map, of course, in the GLS map case, anyway, it's always chaotic. It exhibits robust chaos. But in the case of the logistic map, you have this R parameter, right? What we found was that all the results we got, the Lyapunov exponent was always positive. There was no case where for a periodic we got good results, So that is. Anyway, just comparing deep learning and neural class learning. I'm just comparing them. What are the So basically, what I wanted to argue is that it's an intersection between physics, biology, and computer science, right? This whole field, chaos theory, stochastic resilience, neuroscience, machine learning. There's a lot more work to be done. I'm not claiming that this is the thing, but we don't use any backpropagation, like what Hinton was saying. Start all over again. And the point I wanted to make is that yes, chaos noise does help. That uncertainty in the input is actually good in a very specific sense. Yeah. Two, because the chaos would also be exact. That's a good point. And a lot more work to be done, but we have a collaboration with the Center for Nanoscience where they have these materials that they're growing in the lab, which shows chaotic firing. So we're building a neurocast learning in the hardware, trying to see how it will perform. So we have some initial good results, but we still have a long way to go. But we want to then go full blown neuromorphic computing kind of thing. We have a reservoir computing version of it, but it's too preliminary for me to discuss here. I think I'll stop here, because I had some stuff on. These are all the papers. Important thing is all of it is available on GitHub. So I would encourage people. If you can use it, and as I said, the idea is to improve upon it. I don't think this is the final thing, but chaos. I think because next thing I want to do is can we build a language model out of it? Now that we know that it has been solved by LLMs, can we have a equivalent chaotic network like this, which can solve? We can do language. I think it can be done, but we'll have to work on it again. There are other versions. So people have improved upon our work for adding multiple layers. Remember, we have only one layer. We can have multiple layers, right? Okay. So the monsoon prediction. Maybe I'll just take a few minutes. We just started this work. It's very preliminary in collaboration with the COS Center for Atmospheric and Oceanic Sciences in IISc. So we were just looking at a two-class classification problem. Okay, we were just looking at. You have this 1901 to 2022. We have the long-term mean. Can I just predict 0 or 1? Like, is it lower or above the mean? That's all that I'm trying to do. And we looked at these features, by the way. Again, I'm completely new to this area. Abhishek is doing his PhD there. And so he gave me these 4 SSTs actually, based on, they're all written here. And of course, he removed the linear trend. He removed the linear trend and the mean. And then he gave me the data. And then we trained it. So these are the 4 stuff he gave me, and as I said, the idea is we used 1901 to 2001 for 101 years for training and the 21 years for classification, and we tested with all the algorithms. So this is the initial work. As I said, it's very preliminary, but we could really beat them, but I'm not sure whether it's really great, but we got a 76% accuracy, and these are all the different algorithms. Again, it's just a simple algorithm question. Is rainfall going to be above or below 935.58 mm? That's what we're asking. Yes or no question, right? And if you look at the confusion matrix, right? This is a confusion matrix that we got. What we found is that 2010, we are predicting lesser rain, but reality was greater. And these years, we did the opposite, And the remaining years, we got correct results. But of course, this is very, very beginning. And I don't think we have done, it's just the beginning. And we want to do more work on this. But I think we want to try, because this would work with less data, that's the idea, right? So thank you. And I mean, I took more time, but yeah, I'm definitely not a robot, and hopefully, yeah, none of you are. So thank you.
What about the tower conception, right? You talked about training, the conventional neural net versus your system.
We haven't, yeah, that's a good question. We haven't yet computed any of that yet. But since we are doing only, see, what will happen is, see, we have only one layer. That way it is low. But the only problem is our hyperparameter tuning right now, we're doing a grid search, which is actually very expensive. We're looking at all, we have 3 parameters. So we're looking at Q, B, and epsilon. So that may take some time, So we don't have an efficient way of tuning it, That's the only thing. But otherwise, we don't have any backpropagation and all that, So that way we are faster, but again, we have not done that computation yet. Right now, it's just proof of concept, right? But this thing that we're building in the hardware, there we will do those things, But that's the next step, I would say. I mean, yeah. So you had a question, yeah. No backpropagation, yeah. You saw what we are doing, just the firing and the traces, and we extract features. That's all. So we won't get any weights, right? That's what I'm saying. So just now completely abandon your deep learning way of thinking, You have the input, you have class 0, class 1, right? You're feeding it and the neurons will fire and they'll produce traces. We extract features from them for both classes. And we take and you have 2 sets of features now. I take the mean of them. When the test sample comes, we extract features and we compare which is it close to. It's very simple. We're not doing anything fancy, It's just like feature engineering, that's all, Yes. I mean, it doesn't matter, right? Because any neuron that you use, it will fire and the topological transitivity will ensure that it will detect the stimulus, right? See, the input is coming in, the neuron is waiting, okay? It's waiting with the initial Q value. It's not yet firing. The moment the stimulus comes, it fires. Just like the brain, actually, in that sense, The moment it comes close to that stimulus, it will stop firing. That length can be anything. Some will fire for 100 milliseconds, 100 iterations, some will fire for 1000 iterations. We don't know. Each neuron will fire differently, That's the neural trace. And you can change the map, right? I mean, you can use Lorenz also. You can use anything that you want, as long as you're able to guarantee that you will detect the stimulus. The transitivity part will guarantee you that. The stimulus can be any number, no? I mean, we normalize it to 0 to 1. So the transitivity guarantees that we'll find it. Eventually, we'll find it, no? Epsilon is important because what neighborhood of that stimulus, no? Epsilon is a hyperparameter, so we tune that. We do a 5-fold cross validation, So we do a cross validation. We have 80%, 20%. We take the 80% data, do a k-fold, 5-fold cross validation to figure out the best hyperparameters. And then you apply it to the rest data. So rest is all ML framework only. The algorithm is different. We don't have backpropagation. Yeah, the algorithm is the only difference, We do training testing, cross validation, hyperparameter tuning, all that we do. The only difference is that we are just having those chaotic neurons, which are firing, detecting the stimulus, and then for different classes. And hopefully they are well separated. So think of it like a nonlinear kernel. Another way to think of our method is, it's like a nonlinear kernel, through which we are passing the data. And class 1, class 2 are embedded in some different dimensions and different parts of there's a separation between them, So SVM also will work. That's why we can run our method and then do an SVM, We get that, yeah. Yes, generally it is less. I mean, in most cases we found that with much less data we can learn, Yeah, more data you go. See, what we found is that our method sort of saturates, I mean, to improve it further, we'll have to combine it with ML, Then it will improve. With itself, it's not able to, it sort of saturates off. But it like 98%, 97%, whatever, I mean, it again depends on the task actually. Yes. You can use all the samples also. I mean, you can train it. I mean, you can, that's what I'm saying. I mean, you can use I would sort of, I can give, the GitHub link is there. I'll tell you how to use it also because we want people to try use it, And you can combine it with, see, let's say you're using SVM or using deep learning. You can use our method and deep learning. I mean, you can augment your method with our features. So it works both ways, I'm saying, yeah. Yes. We have only one layer. I mean, there's one work, the Deep Chaos Net, there's a Chinese group, I forget now. They did it on video. They have multiple layers. We did multiple layers also. We didn't get much improvement, The computational resource is so much, and the improvement is very little, So we abandoned that. You can have multiple layers, but you have to be very careful now. Now you're coupling 2 neural networks, They can synchronize and all, so to be very careful. Right. Right.
Sound. I can say whether it's a or play like that.
Right.
Sometimes I can just sense that sound and say, I have to see the.
Yeah, right. You need multiple modalities. Yeah. Correct. Yeah, that's right. Smell and everything. You use all the senses, right? Yeah. I mean, you could. I mean, what we've shown is just the basic I mean, the core of the engine, but you can have other layers, other modalities, maybe. Yeah. It can be done. Yeah. I mean, why not? We can try it. Any other questions? We can. F1 score. I showed you F1 score. You can use accuracy. I mean, yeah, because F1 score is more better. Macro F1 score because imbalanced data. No. Use. No, that's what I'm saying. So hidden layers, we tried. The gain is not much. You do get some gain, but not so much. So we just have one layer. You can have multiple layers, but we found that the paper has it, by the way. The paper has those results also. But multiple layers, the gain was very little, and the computational effort is higher. But I'm thinking that we're not probably connecting them properly. Or see, when you connect these chaotic neurons, no, I mean, as I said, there can be synchronization or near synchronization. So that could be used to our advantage. Right now, we don't know how to use it. So that is one area of research, how to make it meaningful. Right. Exactly. Yeah. So that's what I'm saying. So we solved the XOR problem. We did the universal approximation theorem. We had to do everything what a perceptron MLP had to do. We did all those steps. So we had to. Yeah. I think we have a long way to go. I'm just saying that this is the first step. I would say. Because the brain is doing amazing things. We are nowhere near that. And the noise performance you saw. We're better than deep learning in that sense. I mean that comparison, but not in an absolute sense. I think we'll have to. I mean, in all these examples, what we found, it was the neurons were chaotic. Only then we could do the classification. There was no example where periodicity or anything could do. No. I mean, the neurons are chaotic. No, the firing is chaotic, right? Yeah. Chaos is the heart of the core of the engine, right? I mean, neurons are chaotic. Yeah. Thank you. I think we're well over time, but thanks for patiently listening. And